Okay, before we go into the proof, I want to briefly talk about a principle that we'll need to prove it, called the pigeonhole principle. So what does the pigeonhole principle say? Pigeonhole principle says that given n many pigeons and m many holes, with the number of pigeons being strictly more than the number of pigeonholes, there'll always be at least 2 pigeons that must share a pigeonhole. So here are my 4 pigeonholes, and here are my pigeons. You have to excuse the crudity, I never went to art school, but here are my pigeons. No matter how I'm going to be able to assign pigeons to pigeonholes, so if I put pigeons like this, they're going to have to share. Alright, we'll try again. I'll put them here, put them there. The 3 have to share here. And it's pretty clear to see no matter how I can arrange these 5 pigeons, there's always going to be like 2 that are going to have to share the same pigeonhole, right? And this principle is going to extend if there's infinitely many pigeons. So the principle we care about is going to be given infinitely many pigeonholes, or infinitely many pigeons, I beg your pardon. Given infinitely many pigeons and n many pigeonholes, where n is finite, we're going to get the exact same problem, right? There's going to again be at least 2 pigeons that share. In fact, there's going to have to be infinitely many pigeons that share, but there's definitely going to have to be at least 2 that share. And we're going to use this property, not with pigeons and pigeonholes, but with strings and states. So if we replace pigeons with strings and pigeons holes with states, what we're going to get is, given an infinite collection of strings and finitely many states, there's always going to have to be 2 strings that go to the same state from initial states. Let's write that up formally. Okay, so here's the pigeonhole principle as far as DFAs are concerned. So given an infinite set of strings L, a DFA D, and some state S of D, there exist strings alpha and beta that are in the collection of strings L, such that alpha and beta are different, and the state you go to from the state S consuming alpha is the same state you go to from consuming beta. So that is to say, from the state S, alpha and beta take you to the same place. Okay? So let's prove this. So D is a deterministic finite automata, which means necessarily it's got finitely many states. Let's say it's got n many states. Let's let S represent any state of D that you like. So we'll just fix some state S of D. Now I'm going to take any n plus 1 unique strings, alpha 1, alpha 2, yada yada yada, alpha n plus 1 from L. So this here is n plus 1 strings. They're all from L, and they're all different. They're all different to each other. Now consider this collection here, n star S of alpha 1, so that is the state that alpha 1 takes you from S. The state alpha 2 takes you from S, blah, blah, blah. The state alpha n plus 1 takes you from S. This whole thing here is a collection of n plus 1 many states of D. Now, since D only has n many states, and n plus 1 is bigger than n, then this collection here must have a duplicate somewhere. That is to say, there must exist 2 dissimilar strings alpha I and alpha j, such that the state that alpha I takes you from S is the same state that alpha j takes you from S. So what does that imply? That means there exist strings alpha and beta in L, such that alpha is not equal to beta, and alpha and beta take you to the same state from S as required. So that's the formal proof of the pigeonhole principle for DFAs. You give me an infinite collection of strings, you give me a DFA, and you give me some state of that DFA, I can always find you some strings alpha and beta in that collection, such that alpha and beta are different, but from the state S, alpha and beta go to the same place.